Hey, welcome back. This is 3.8 in calculus. We're still working Newton's method. And what is Newton's method? It's a way of finding x-intercepts, okay? And you're using calculus. So it finds x-intercepts. Okay, so first we'll look at kind of a visual interpretation of Newton's method. Let me try to draw this. This is always an issue, trying to get it drawn correctly. So we have some weird graph, and we want to figure out what is that place where it's hitting the x-axis, right? And I have to do it in a couple iterations. So I'm going to, I wonder if I can copy and paste this thing. I don't know. I get carried away with all the baloney. Okay, so I'm going to do like 4 of them. It's supposed to be the same graph drawn four times, okay? So something like that. All right. So to find this x-intercept, what you do is kind of just randomly pick an x value, okay? And we'll call it x sub 1, okay? We'll take that x sub 1 and go up to the actual graph, okay? And at this point, you're picking off, you're going to form the equation of a tangent line, okay, like here. You need the derivative to do that. So it has to be a differentiable function, okay? Once you get that, you extend that tangent line to the x-axis, okay? So maybe it would be in here somewhere. And then that's going to be your next kind of point, okay? So this will be x2, okay? So let's then do the same process over, right? So we take x2, we go to the graph, create a tangent line, and extend the tangent line to the x-axis. And that will be our next point. Okay, so this will be x3. Okay, and then we have our x3 here. And we extend, we go to the graph again. So go up to the graph and form the equation of a tangent line and extend it to the, and look how close it's getting to the actual intercept if we do this over and over. So that would be our x4. So x4 here, you extend it to the graph, you put it in green, and then form a tangent line, and that gets closer and closer. Okay, so the idea is you pick a point, you create a tangent line to the graph at that point, you extend the tangent line to the x-axis, and that becomes your new point. Okay? And then you take the tangent line at that new point, extend it to the x-axis, it hits, that becomes your new point. And it creates a sequence of values that hopefully converge to the intercept. Okay? And it doesn't always work, but sometimes it does, and that's a good day, right? Okay, so we need not just a geometric interpretation, but we would rather have a formula for dealing with this. So that's what we're going to work with right now. So the formula for Newton's method. Okay, so we just want to translate what we just did visually into algebra. Okay, so you can experiment with things visually and then try to transform it into a more rigorous environment of algebra. Okay, so first, what did we do? We picked a random x value, pick x1, and then secondly, we created a tangent line at that point. So create equation of tangent line at x1 comma f of x1. Okay, so to create a tangent line equation, we need 2 things. We need a point and we need a slope, right? So our point, of course, is what we just noted, x1 comma f of x1. That's easy enough. The slope, we need a derivative. We need the derivative of f at x1. Okay. Then we could use the point-slope formula. Okay, so if you remember to the top right here, y minus y1 equals m times x minus x1. Okay, that's our point-slope formula. Okay, so we plug all this into that. I'll have y minus y1, which is in this case f of x1, equals the slope f prime of x1 times x minus x1. Okay. And then I'm going to solve this for y. So I have a nice equation. Y equals f of x1 plus f prime of x1 times x minus x1. Okay, so what did I do then? So I got the equation of a tangent line, like this blue guy on the top left here, tangent line. And so what did I do? I extended the tangent line to the x-axis and found that point. So what does that mean? That means I basically set the tangent line equal to 0 and solved for x. Okay, so that'll be my next step. Set tangent line equal to 0 and solve for x. Okay, and then that becomes your next point. Right, we have y, we set that thing equal to 0, so just replace y with 0. And then we have f of x1 plus f prime of x1 times x minus x1. And then we're going to solve for x. Okay, so let me put it in blue. I want that guy by itself. Okay, so I'm going to distribute. Then I'm going to move this term and this term to the other side and flip-flop sides. Should be f prime there, if that's not clear. Divide by f prime of x1. And the first term, that, it's so in the first term, the f prime of x1s will cancel. I'll have x1, then minus f of x1 all over f prime of x1. Okay. This new x value then, because we know what x1 is, we know f of x1, we know f prime of x1, we'll have a number for that, and that will be our new starting place. Okay, so once you get this new x value, you'll go back to the previous step and start all over. Right, so you'll go back to step 2, create an equation of a tangent line there, then set it equal to 0 and solve for a new x, and that will be x3, and so on. Okay, so in general, our formula, it's called an iterative formula. It will be x sub n plus 1 equals the previous x value, x sub n minus the ratio of f of x sub n and f prime of x sub n. And that thing there is Newton's formula, or Newton's method formula, or whatever they call it. Okay, so and applying this, so application of this formula, how are we going to do this? So first you're going to make an initial estimate for x1. So estimate x sub 1. Okay, just use an educated guess. You don't want to be too far out, too far away from the intersection point. But what do I know how to stop? Am I just going to keep doing that forever? Well, you're going to stop when the difference between two consecutive values is less than whatever value you're given, right? So the book will give you some desired accuracy, and as soon as you see that the values aren't basically changing anymore, that will give you your final approximation, which will be the x sub n plus 1. Okay, so that's how you know when to stop. The first couple problems are just going to have you do the process, not necessarily stop somewhere. So in the first one, they just want you to complete 2 iterations of Newton's method. Okay, so For example, we have f of x equaling x cubed minus 3 and x sub 1 equals 1.4. Okay, okay, so we start with x sub 1, 1.4. We're also going to need the derivative, so we might as well get that. F prime of x is 3x squared, and then the derivative of minus 3 is 0. Okay, we got it. So x sub 2 is, well, x sub 1, which is 1.4, minus f of 1.4 divided by f prime of 1.4. Okay, so that will equal 1.4 minus, what is it, 1.4 cubed minus 3 all over 3 times 1.4 squared. And my calculator is telling me that this should be about 1.44354. X sub 3, so when I'm working with my calculator, I have like a TI calculator and it has like a remember answer button. So what I do, instead of worrying about, you know, where am I going to approximate, what decimal point should I approximate to, I just keep the answer in the calculator and rewrite it that way. So in my calculator, I literally, in my next step, type in answer minus answer cubed minus 3 all over 3 times answer squared. And then calculator will plop out that number. Turns out to be 1.44225. Okay. All right, so I did it twice. I'm happy. Hopefully the book's happy about that. And if I want to do more and more, if you set up your calculator right, you can have it kind of just push enter over and over, and it'll keep giving you numbers. Okay, so you can automize it depending on your familiarity with that kind of stuff. Okay, let's look at another one. So this one gives you an accuracy level. So do Newton's method until the error. So work until the difference between two consecutive values is less than 0.001, which basically just means keep doing it until this place doesn't change anymore in your answer. Okay, so let's take a look. This is number 11. Well, it used to be number 11. We'll just say it's an example. They give us f of x equals x minus e to the negative x, and then we're going to need the derivative. F prime of x is 1 minus e to the negative x times negative 1, which will be plus e to the negative x. Okay. I need an approximation for x1. Okay. If you were to draw e to the negative x, it would be just a rotation about the y-axis, right, of the exponential growth function. Then negative e to the negative x rotates it about the x-axis, right? So it would go down like this. And then if you add in an x, it's going to, on the left, kind of shift everything down like this. And then on the right, it's going to kind of push everything up like this. Okay, so that should be a good estimation of the graph. And I'm thinking, where does it hit 0? It's probably around 0.5, but I don't know. Okay, so it's around 0.5. So I'm going to let x1 equal 0.5. And clearly you could do your calculator, but somehow I think using your calculator is kind of cheating somehow. But when push comes to shove, just use your calculator to get a guess. All right, so x1 is 0.5. x2 then is 0.5 minus 0.5 minus e to the negative 0.5 all over 1 plus e to the negative 0.5. And my calculator is saying that's about 0.5663. Okay. Go on to my next one. X3 is going to be basically that answer minus that answer minus e to the negative answer all over 1 plus e to the negative answer. And my calculator is saying that is about 0.5671. So you want these numbers here to not change as you go from one to the next. And when that happens, then your accuracy will be less than 0.001. Okay. Okay, so let's try x4. Plot that in my calculator, get answer minus e to the negative answer all over 1 plus e to the negative answer. And I'm getting 0.5671. Okay, so good. As long as that thing doesn't change, you're done, and that can be our answer. Okay, so we think this equation or this function hits the x-axis at about 0.5671. Okay, so the intercept, the x-intercept is about 0.5671. Okay. Okay, great. This method won't always work. Obviously, if you're picking out a point that's way far away from the actual intercept, it'll probably fail. In those cases, what you want to do is maybe pick a different x starting point. And then secondly, there are kind of some conditions you can check if things get really bad. So conditions for convergence, which just means the number gets closer and closer to something. It's like an idea of a limit. Okay, so the conditions for the convergence of these numbers is that the absolute value of this expression has to be less than 1. Okay, so this I'm not gonna get carried away with that, but if things really go wrong in your life, you may have to investigate that formula. Okay. Okay, I won't force you to. Let's look at an example where stuff does not work, and so you get an idea of one at least circumstance of failure. 6x minus 1. We want to start at x1 equals 1. Okay. Okay. So I need the derivative. Y prime is going to be 6x squared minus 12x plus 6. And then I'm going x1 is 1, and then x2 will be 1 minus. Plug 1 into y, so you get 2 times 1 cubed is 2, minus 6 times 1 squared is 6, plus 6 minus 1, all over 6 times 1 squared is 6, minus 12 times 1 is 12, plus 6. And that'll be 1 minus 6 minus is 0, 1 all over 6, 12, oh, 0. And there's the bad news. So this is bad. You cannot divide by 0. So we would have to maybe start at a different starting point. Okay. Okay. One final type of question, finding the intersection point of curves. And what this demands is that you reinterpret the intersection as finding an intercept. So our example here, we want to find the intersection of f of x equals x and g of x equals tan x. So if you think about finding intersections, in general, what we do is set the equations equal to each other, right? So setting them equal to each other, x equals tan x, we can note that this is the same as x minus tan x equaling 0. So ultimately what this tells us is that we want to find where the function, so we want to find where this new function, we'll call it h of x, which equals x minus tan x, hits the x-axis. So you've changed one problem, this problem of finding intersections, into a problem of finding a 0 or a root. Okay, so once you set that up, then you could go to your calculator and get look at the graph and then find a point that looks close to the intersection, and then use Newton's method to figure out your answer. Okay, so you know, we're dealing with h of x equals x minus tan x. I need the derivative. H prime of x will be 1 minus secant squared x. And then I need a guess for my initial contact, my initial assumption. And I picked 31 pi over 21 just because I thought for some reason that would be very close to the intercept. And then I went and started iterating. Okay, so 31 pi over 21. X sub 2 is basically x sub 1 minus f of x sub 1 all over f prime of x sub 1. And in my calculator, I got 4.5887. Okay. And I'm not going to, you could do it on your own, but I had to go pretty far to x6 to get a good 3 decimal place approximation. So my x5 was 4.4937, and then my x6 ended up being 4.4934. Okay. Okay. So once I got the third decimal place in line, I think that's the error they wanted in the book, and I stopped there. Okay. So let's call it quits for today, and I'll see you next time.